Hello everybody, my name is Simone Meneghin and today we will see how to test a transformer differential protection using our software TDMS Pro. And with this software we are going to test a very famous relay, and this relay is the General Electric T60. Before to start, it's good to make a list of few points that will be helpful to understand better what to expect from this presentation. So what you will find in this presentation is a sort of guideline in order to understand the most important concept that must be known if you want to test properly a transformer differential protection. You will find also mathematical calculations and examples in order to demonstrate that the differential current are calculated. And after having discussed the concept and the concept learned will be used for the test of General Electric T60 relay. You might disagree on the mathematical notation that I used to describe all the formulas, and maybe you might disagree on the logical sequence of the concepts. But trust me, there is no a better way than another to present all these concepts. So my suggestion is to read, go through all the slides. From time to time, maybe you have to think a little bit more. Maybe you have to go back and forth from many slides. But in my opinion, all the relevant and most important concepts are present. And then it's a good basis to start knowing better how to approach a transformer differential protection. Last but not least, you have to be familiar with the vector and matrices, and of course, the basics of the protection relay testings. The concepts we are discussing today are quite complex, so I think it's good to have a cup of coffee that will surely help. Let's first introduce the power transformer. So the power transformers can have 2 sides or 3 sides. So we will discuss the case of 2 sides only for the sake of simplicity. So this is the power transformer with a high voltage and low voltage side, and the current, the load current is flowing in this example, is entering the high voltage side and going out from the low voltage side. This primary current is flowing also in current transformers, and the secondary side of these current transformers are connected to the relay. The notation I used is a capital letter for primary current and small letters for the secondary current. The first important concept to be understood is that the differential current is a sum of vectors. So sometimes people can think that to see a plus into this formula is a mistake, but it's not a mistake because the differential current that bring the concept to see a minus here is an information that is inside the direction of the vector. So we have to also to agree about a convention. All the currents that are going into the transformer are positive. All the currents that are going out from the transformer are negative. Okay, so the minus is inside the direction of this vector. So in normal working condition, the differential current is 0. This is the base of the following discussion. So we have to do our best in order to keep this number equal to 0 when the power transformer is in service without faults. We know that due to the turn ratio of the transformer, the value, the magnitude of the current at the two sides is not the same. In particular, the magnitude of the high voltage side is less than the magnitude of the low voltage side. We are talking about vectors, so the sum of vectors can be seen as in this way. So this red vector is the sum of these two vectors, and we can see that the magnitude of this red vector is not 0. So we have to apply the so-called compensations. So we have to compensate, first of all, the magnitude of these two currents. So we can think that these two vectors are multiplied by factors, and these factors are numbers, the simple numbers. To be more precise, real numbers. But this is not enough, because we have also to compensate the phase shift. Otherwise, this vector can't be 0. Okay, so the phase shift is now compensated. You can imagine that we have applied something that modified the phase shift. Now they are in phase. But again, this is not the end of the story. We have to also consider the direction, the same concept that I explained before. The current that is flowing into the transformer is positive, and the current that is flowing out is negative. Or in other words, they have opposite direction, then the two arrows are like this. So in this case, the differential current is finally equal to 0. So I repeat once again. We have to apply at least two compensations. The first one is a magnitude compensation, and the second is a phase shift compensation. The last is not a compensation, is only the Kirchhoff law, basically. Okay, so we start to see that the differential current formula start to be a little bit more complicated. So it's not only the sum of the primary current and the secondary current, we have also to consider the multiplication by two real numbers. A little bit more complex is the phase shift compensation. So we are talking about angles. So every time we have to agree about a reference. Without a reference, it's not possible to define the value of the degrees, for example. If I say 20 degrees or 30 degrees, is a meaningless concept if I don't say 20 degrees in respect to what reference. So we start to learn about the concept of reference winding. So we have to agree who is the vector that will be my reference. In this example, I decided that the reference winding is the high voltage side. So the secondary side current must be rotated by, in this case, 30 degrees clockwise. This phase compensation is performed by specific matrices. So this vector for the high voltage currents must be multiplied by a matrix. I use the notation of a capital letter for H and the capital letter L for the low voltage side. I also used colors, so the same colors will be used also in the next slides. So the blue will indicate values and parameters regarding the high voltage side, and the green color for the low voltage side. But there is the last compensation to be taken into account, and is the zero sequence compensation. So first of all, we have to say that the zero sequence compensation is necessary only when at least one of the sides of the transformer is connected to the ground. For example, if you have a Y side, the neutral can be connected to the ground. If this is the case, and if there is a single phase to ground fault, there is a current that is flowing into this loop, in particular is flowing also into the neutral, and this is a zero sequence current, basically. So this brings a zero sequence current that is not equal to 0. But the zero sequence current cannot exist in delta connected sides. So the zero sequence current exists on this side, but it does not exist on the other side. For this reason, we have to compensate the zero sequence. Otherwise, in case of faults that are not inside the transformer but into the line, where for which the relay should not trip, without this compensation, it's possible that it trips. And this is something that you would like to avoid. The zero sequence compensation needs matrices. Again, I anticipate that this matrix for the zero sequence compensation most of the time is the same matrix that is performing the phase compensation. So these two concepts must be considered more or less the same concept. In particular case, they are different, but in most of the cases, they are the same. So I repeat once again, in most of the cases, when you do a phase shift compensation, you are also doing, in the same time, with the same matrix, the zero sequence compensation. Okay, this is the most generic formula we can write for a differential current. So the primary side current are multiplied by a compensation matrix and a compensation number. This number is to adjust the magnitude, and the matrix is here in order to compensate the phase shift and the zero sequence current if necessary. Just to say it one more time, and for the last time, we have a different magnitude at the two sides because of the turn ratio of the power transformer and also because of the turn ratio of the current transformer. We have also to consider this in order to estimate what is the right value of K1 and K2. In case there is a path for the current to flow into the ground, then you have to apply a zero sequence compensation. And in the end, if the vector group is not the YY or delta delta group, YY0 and delta delta 0 group, then you have also to apply a phase shift compensation. The full list of compensation matrices are typically present in the user manual of every relays. In this slide, you will find the most common matrices. Okay, the unit matrix basically is doing nothing because it's like to multiply by 1 a number. So the unit matrix is doing no phase compensation and no zero sequence compensation. Then you can find this type of matrix. This type of matrix is not doing a phase compensation, is doing only a zero sequence compensation. And the last two matrices are performing both phase compensation and zero sequence compensation. This one in particular is also applying a 30 degrees clockwise rotation. This one, a 30 degrees counterclockwise rotation. Now we are trying to demonstrate that these matrices are applying a phase rotation. We will not demonstrate that these also remove the zero sequence. You can find this demonstration easily in the web. So in order to don't make this explanation too heavy, I decided only to demonstrate that this matrix is doing a phase rotation. We don't have to forget that we have always to define who is the reference winding for the phase shift compensation. In this example, the phase shift compensation use the low voltage side as a reference. So the low voltage currents are multiplied by the unit matrix. These are the same equations, but more explicit. So in order to go from this notation to this notation, we have to apply the rules of the matrix multiplication. So why this is like this? Because we have to start from this, then we have to multiply this element by this element, okay, and is this element. Then this element is equal, must be multiplied by this element, and then we have this element. The third one is not present because it's multiplied by 0, so it's not present in this formula, and so on. For this part, let me say that it survives only the phase A current because it's the only one that is multiplied by an element that is different than 0. I'm saying nothing special. This is algebra. Okay, so basically, if I'm doing this, I'm applying a phase rotation. And we can see, so what we are going to do is to move these vectors counterclockwise of 30 degrees. So this must become a vector like this. The same for the other two phases. So let's see how to do it. So we have to keep in mind these formulas. So in order to have a differential current for phase A, what I have to do is to take the phase A current and I have to add the minus B phase current. It's important to understand that this minus does not mean the difference of two vectors. This is the sum of a vector with a minus in front. So this is the correct way to see this formula. Otherwise, this will not be the vector that we are going to use, will be another one. So please keep this in mind. This minus is a sum of vectors. The minus comes from the direction of this vector. Okay, but we have also to consider that there is a square root of 3, in particular 1 over square root of 3. This is present, this factor, in order to reduce the amplitude of the vector, because I don't want that the vector will become bigger. I want to keep the same magnitude. I just want to rotate of 30 degrees. If I do the same for the other phases, the final result is something like this. So if you compare the phase shift of these three vectors, you see that are exactly the same phase shift of these vectors. Now we see a second example. So the vector group of the power transformer is the same, so is a YND11, but the reference winding now is the high voltage. Okay, this means that I have to apply the zero sequence compensation on the high voltage side because I have a neutral connected to the ground. So if we go back to the previous example, you can see that the reference winding in this example has been multiplied by the unit matrix. But in this case, is not possible. Otherwise, the zero sequence will not be compensated. Why I was not compensating the zero sequence in the previous example? Because in delta side, data connected side, the zero sequence simply does not exist. Okay, so applying the same calculation as before, so I have to calculate all, I have to repeat all the passages. What I will find in the end is that this is not doing any phase compensation, any phase rotation, but this low voltage current are rotated by 30 degrees clockwise. So doing the same calculation, the same passages, I mean, that we did before, if you repeat the same exercise, then you will see that this is the final result. But warning, if you do the zero sequence compensation, applying this matrix introduce another factor that is going to modify the amplitude of the currents, and this must be taken into account. If you are not taking this into account, then the fault current that you are going to calculate in order to test your relay will be wrong. Okay, so you can see how many concepts must be known and clear before to find the numbers to the current to generate with your test set for a proper testing. This is another table that is trying to resume the most common situations. So in case of a vector group YND11, where the phase shift compensation use the low voltage winding as a reference, the matrix to be multiplied to the YN side is this, because I have to apply a phase rotation. Vice versa, if the reference winding is the high voltage winding, then this is the matrix to be applied because I have to compensate the zero sequence. On the low voltage side, I'm not multiplying by the unit matrix, but I'm multiplying by this because the reference side is the high voltage side. Then I have to rotate the low voltage current. Then if you pay attention in the third example here, the neutral is not connected to the ground. This means that I don't need to compensate the zero sequence. So even if the reference winding is the high voltage winding, then I have only to multiply by the unit matrix. Okay, so I understand that this concept can be complex if this is the first time that you see. You have time to, in the end of the webinar, to read the documentation. So this presentation is available in the hands-out section of the dashboard of this GoToWebinar platform, so you can download it now. Or you can review the webinar. In a few days, there will be available in our YouTube channel, but you will receive a follow-up email where you will find a link where you can download also the video of this. So don't worry if all these concepts seems very complex to you. It's enough for me that you start being aware about the complexity. In order to dominate all these concepts, you really need a lot of exercises. But at least with these slides, you have a guideline and you know on what to focus mainly. Now we have to see how the fault current are calculated, because all the matrices that we saw since now are not related to any fault current. This is just a matrix that you have to use. But these are the real currents, and the real currents depends on the power transformer vector group, which phases are involved in the fault, and also which side of the parent transformer is involved in the fault. Because it's not the same if the fault is on a Y side rather than a delta side. For example, if the single phase to ground fault is on the high voltage side and this is a YN side, so the current can flow only in one phase. In this example is the phase A. You can see the current is flowing only in phase A. But due to the vector group and how the windings are connected internally, there is current also in the secondary side. So the the fault current is transformed by the transformer. So it's not possible to have zero current on this side. In particular, we have to pay attention that we have one current in the high voltage side, and it's also not possible to have only one current in the secondary side. The current will be two. One is flowing into phase A, and due to the delta connection, one current will flow out from the phase C. So if I want to represent this situation, I have to substitute these letters with these numbers. So 1 represents the fact that the current is present. 0 represents the fact that the current is not present. In this case, the only not present current is the one in phase B, and the two currents of the other two phases are opposite in phase. That's why 102 has a minus. Okay, I decided to use just 1 and zeros for the sake of simplicity. This number should be the proper number that comes from the calculations that take into account the current transformer ratio, the power transformer ratio, the power of the transformer, and many other things. But this is just adding complications, is not helping us to understand the concept. So from now, we only use ones and zeros. Must be understood that in this case, for a single phase to ground fault, there will be not only one differential current that will be measured by the relay, but two. And the second differential current is clear why is present, because we have current in phase A and current in phase C. In particular, if we go through all the passages, we will find that we have differential current A that is equal to the differential current B, but with an opposite direction. So regardless the direction, this minus, so if we just consider the magnitude of the differential current, we see that in this particular case, phase A and phase C measures the same differential current. So I repeat once again, the fault current the fault involves only one phase in one side, but the differential currents will be two. Okay, this is a screenshot that comes from one module of TDMS Pro. This is a quick way to generate current. Here you see that I tried to generate 1 amp in phase A. Before I have to clarify that I1, I2, I3 are connected to the high voltage side of the relay, or in other words, the primary side, and I4, I5, I6 are connected to the secondary side. So one current in one phase on the high voltage side, and two currents in phase A and C on the low voltage side. If I'm doing this, what I will get is a differential current in phase A, a differential current in phase B with the same magnitude and opposite in phase. This is a demonstration that this is exactly what the relay is doing. If I want to see these points into the differential characteristic, I can see it in this way. So I can imagine to have a differential characteristic per each differential element. So the differential element will measure this differential current. The differential element B will see 0, and the differential element for phase C will see the same point as in phase A. I forgot to highlight the fact that this situation is true only if the reference winding is the low voltage winding. Because if I change the reference, I'm also changing the matrices. And that's why I'm explaining a second example. So now the situation is the same. There is a single phase to ground fault on phase A, on the high voltage side, but I'm applying different calculations. It is enough to change the reference winding, then you can see that the differential current will not be only 2, but they become 3 with this magnitude proportions. So phase A will see the double of the other two phases. This is important because this can bring to some strange effects that we will see later. Just a disclaimer, this example is not applicable to General Electric T60. So this is not a calculation that this relay will do for a very simple reason, because if there is a delta side in the vector group, this will be the reference winding. So it's not possible to set into the relay the possibility to change. So if there is a delta side, this will be the reference winding. So in this case, so don't try to do it and look for this situation with this vector group, because with General Electric T60 simply is not the situation. But this is important. The phase A element will measure the double of the other two elements. So if I decide to test this particular point, there is the possibility that the other two elements will fall into the trip area. So I generate the currents in order to see this value in element A. I expect that the relay is not tripping, but what happened actually is that the relay is tripping because of the other two elements that are into the trip area. This creates unexpected trips or unexpected interventions. So I want that every time I simulate values for no trip area, the relay should not trip. Otherwise, it will be confusing. So there is a trick. So this is, since this is a normal behavior, the trick is that I will modify only for particular cases, and the particular cases are of this nature. I will draw a, let me say, a virtual characteristic that will always keep all the points of the trip area above this line, and vice versa, all the no trip, all the values that are not producing trips will remain below this line. Okay. And this is what actually the software is doing. So this is an example of nominal characteristic, but if I select that I want to simulate faults on, let's say, high voltage side, and in the end of the calculation, the differential current are one, the double of the others, then what you will get is a virtual characteristic. So it's not strange that in some situation in the software you will see something that you do not expect. So if this happens, I repeat once again, is normal and is due to the reason we explained before. And this is the test setup I'm going to use right now. So I'm now using the software, TDMS Pro, that is connected to the DRTS66. The DRTS66 will generate 6 current connected to the General Electric relay. And then we are going to play a little bit in order to demonstrate the effect of these compensation matrices.